Welcome back. In the previous video we have discussed the record conversion efficiencies for the best performing solar cells of the various PV technologies. And here we touch up the weak point of the NREL efficiencies chart. It's basically comparing apples and oranges. The efficiencies are reported for small lab scale devices with a size of only 0.1 square centimeters, and some are reported for large 6-inch wafer size solar cells corresponding to an area of 250 square centimeters. This is at least a difference of 3 orders of magnitude between the lab scale cell and the wafer cell. Therefore, I prefer to present the record efficiencies per PV technology as a function of the device size. So the learning objective of this video lecture is to understand how the typical conversion efficiencies of technologies vary with the device size. In this graph, you can see on the vertical axis the conversion efficiency and on the horizontal axis the area of the solar cell device. A typical lab cell device has an area in the order of 1 square centimeters. Wafer sizes are in the order of 100 to 400 square centimeters, and module sizes are larger than 1 square meters, or in other words, larger than 10,000 square centimeters. This graph nicely demonstrates the level of maturity of a PV technology. A mature technology is a PV technology that has a limited loss in conversion efficiencies when going from a small lab scale device to a large scale sized modules. Let's consider the first dominant technology, which is crystalline silicon. The multicrystalline silicon efficiencies go from 22.3% for 4 square centimeters down to 21.3% for a 6-inch wafer size solar cell, and next down to 90.9% for a PV module of 1.5 square meters. From wafer to module, 1.4% is loss. The losses are a result of lower coverage of the active area due to gaps between the solar cells and the electrical resistivity losses due to the interconnection between the cells. A similar trend is shown for the IBC HIT technology of Kaneka. The record efficiency is 26.81% for a wafer size cell based on the IBC architecture, and decreases slightly to 24% for a 1.3 square meters module. This represents a loss of 2.4% from cell to module. Let's consider the 2 PV device structures for the 3.5 PV technologies that result in both lab scale devices and small sized modules. These architectures are the thin film gallium arsenide PV modules from Alta Devices and the indium gallium phosphide gallium arsenide indium gallium arsenide triple junction from Sharp. It can be clearly seen that the negatively slope in this plot is larger than for the crystalline silicon technology. This suggests that the upscaling of the single and triple junction device to module size is more challenging. This results in more efficiency losses. The indium gallium phosphide gallium arsenide indium gallium arsenide triple junction module has a size of about 858 square centimeters, which is about 30 by 30 square centimeters. Note that for such typical small module size, this triple junction has the highest efficiency of all PV technologies. Let's consider the thin film PV technology, and we first look at the thin film PV silicon technology. The green line at the bottom. The line hardly has any slope, indicating that the processing of this technology is rather mature. The record lab cell of about 1 square centimeter has a record efficiency of 12.7% and is based on the amorphous silicon nanocrystalline silicon tandem cell. The module with a size of 1.4 square meters is 4 orders of magnitude larger and has an efficiency of 12.3%. This represents a small loss of about 0.3.4%. This demonstrates that the processing technology of thin film silicon PV technology is very mature. The thin film silicon processing methods are used for other industrial applications like large display technologies as well. The disadvantage of this technology is the lower stabilized module efficiency when compared to the other dominant thin film PV technologies like CIGS and cadmium telluride. The CIGS technology shows a 23.35% record efficiency for a cell of about 1 square centimeter, while Solar Frontiers have demonstrated module efficiencies of about 18.6% with a size of about 1 square meters. This still shows a significant drop of about 4.8%. An important factor that plays a role is that the various CIGS module manufacturers use different CIGS processing methods. Therefore, the intellectual property needed to reduce the upscaling losses has to be mainly developed in-house at the company. The record efficiency of lab cells and modules based on cadmium telluride are all achieved by the leading company in this technology, First Solar. The record efficiency drops from around 21.0% for a lab cell of 1 square centimeters down to 90.5% for a module with a size of 2.3 square meters. This is a relatively smaller loss of only 1.5% in reference to the CIGS PV technology. If we look at the emerging technologies that have resulted in small module designs, we see that the single junction organic PV technology goes from about 18.2% for a 0.03 square centimeters lab cell down to 8.7% for a small module size of around 800 square centimeters. This represents a 9.5 absolute drop in performance. An additional challenge for the organic PV technology is that these reported efficiencies are not stable. Under operation, the module performance will significantly degrade as well. The line corresponding to the perovskite technologies shows that this technology is not fully mature yet as well. Record efficiency above 25.7% for extreme small lab cells of 0.1 square centimeters have been obtained. The conversion efficiencies are reduced when the size of the perovskite cell is scaled up with a factor of 100 or even 1000. Best efficiencies for an 800 square centimeter module are 17.9%. Note that the perovskite technology also suffers from instability issues. The performance degrades in time. So perovskite PV technology still faces significant challenges to prove that it can become a mature technology to be commercialized. We also discussed that many companies, research institutes and universities are exploring a high bandgap perovskite solar cell on top of a crystalline silicon bottom cell. Currently, no module efficiencies are available yet to add them to this plot. This figure shows record efficiencies. Are these the same efficiencies as the model efficiencies in mass production? I will discuss that in the next video lecture. So see you in the next video.